Hello, everybody. I'm Paul Profisi. I'm from the DPF team, developer. And my goal today is to present very quickly what DPF is and what the PyDPF libraries are. So we're going to talk about the DPF fundamentals, what it's useful for, what it looks like, and the framework that comes with it for those of you who don't know about it. And then the Python ecosystem we call PyDPF around it, and then a bit about what to expect next for DPF. So what DPF is, you've seen in the different other PyAnsys libraries that have been presented before that they are mostly all linked to solvers and existing products. DPF is a bit different because DPF is sort of a product, but that's never been exposed via a UI or an application in the Ansys product library, let's say. So I wanted to go a bit over what it is because most people may not know about it. The context of the creation of DPF, which stands for Data Processing Framework, is to enable more simulation, automate more, easier access to your result files and things like that. Basically, the idea was that Ansys provides a lot of simulation solutions for most applications, but we have all different file formats, different data models, different translation operations which are necessary to go through from one product to another and these sort of things. So the idea was to basically build a single framework with a single data model, which would be able to treat any sort of simulation data or data at large and process it to operate on it and transform it any way you would like. All of this within a framework which would enable users to build upon it, to create their own operations and their own data processing workflows. And of course, we are at Ansys, so we optimize support for Ansys data, and we aim at extending support for all of the different Ansys result files you could imagine. What DPF is for is at large, basically processing data. So this can be, for example, for post-processing, where you have your result files here, and then you want to access your simulation data via a script and manipulate it in some way. So, for example, perform filters or select an element or some criteria, for example, a head injury criterion, or compute any sort of criteria that you want, and then visualize it or export it to another format such as VTK or CSV or whatever you can imagine. Sorry, I'm going a bit fast, but it's not limited necessarily to the post-processing phase. You can also imagine pre-processing workflows, for example, with meshing steps and let's say filtering based on positional node coordinates or things like that, and to prepare the data for another solve. For example, we have many use cases where we couple solvers and different steps, simulation steps. Here an example where you couple a reduced order modeling with a fluent simulation. So you prepare your reduced order model, but then thanks to DPF workflows, you can directly link it to a fluent simulation as an input, let's say, or as boundary conditions. So this is the sort of stuff that we managed to do with DPF. So it's all about making Ansys products communicate between each other and allowing users to process their simulation data. So as a conclusion to what DPF is, it is a set of shared technology components so that we don't have to reinvent the wheel every time we build something, in a consistent framework across Ansys products, which enable you to treat your data and operate on it. It is a data processing toolbox made of different operators. We're going to see what they are later, but basically little black boxes you can use to perform operations. You can think of them as functions, which you can set up and connect to build workflows. And of course, it is a framework so that you can build your own solutions upon it and enable more people to use your simulation results in simulation processes. I'm going to go very quickly on the DPF fundamentals because it is all explained in the doc, and the goal here is to not necessarily go over everything very precisely, but as I said in the beginning, DPF, the original aim was to provide a common data model for all of the different results that we could have, or the different data we can manipulate at Ansys. And the idea is that you have basically fields of data, which can be displacements across nodes, which can be acoustic levels over frequencies. This is all a field. You can think of them as matrices or as NumPy arrays. This is the equivalent. And then you have what we call operators, which are functions or bricks which perform data. You can give them different inputs and they will give you different outputs. So combining the two, you can create workflows basically. This is a small slide on fields, the fact that we separate metadata like a unit type, physics type, and the mathematical data, which is about the raw data, like the actual values. You can see here on the right what it looks like. As you can see, the field is actually a wrapper on NumPy arrays with some metadata specific to simulation. Here we can see a field which is located on nodes. Values are in meters. They exist for a certain number of entities which are nodes, and they have three components, and then you can have a preview of the different values on your field. I like this slide because it gives an overview of the different concepts that we have to define a field. So we have the raw data as dimensionality, homogeneity, support, so what it applies to. And again, all of this is explained in the documentation, but I wanted to give you a quick peek at what it looks like, just to explain that the difference, for example, with SciPy or NumPy or other generic Python libraries you could find to manipulate data is that here you will have specialized APIs for manipulating simulation data, and we have different objects specific to let's say a simulation data. We do also have the notion of collections of fields of data. You can organize them any different ways you want. For example, if you have multi-step analysis or multi-frequency analysis, of course, we have the ability to describe all of this and to manipulate it in a coherent way. So again, going quickly over this, basically, we define different labels for your data, which you can then select and manipulate according to what they are labeled with. You can think of labels as like a time ID, or maybe an element type, or maybe a shell layer ID. Any kind of thing you would think of. So it's pretty versatile. The operator is basically the analog of a little electronic component where you have input pins and then output pins, and then you can chain them and organize them so that your data flows from, let's say, operator to operator and gets transformed along the way. You can think of this as functional programming or whatever analogy you would like. And the point I wanted to make is that the goal of DPF is basically to not reprogram the different operations we could imagine every time. Not every product has to reprogram what an FFT is. The idea here is to have a common library with usable operations, and we have already quite a few available. Here is a quick peek. You can see that again in the documentation. You can go through the list of available operators. We have operators to work on, let's say, geometry, to extract results from Ansys files. We have averaging operations, mathematical operations, of course, operations regarding different invariants you can have in simulation data, and then filtering, mapping also, different operations on the mesh, and other operators, let's say a generic operations you would want to do on your data. So again, you can link all of those to create what we call workflows. We do have a UI coming, let's say, quite soon, which will enable you to build these workflows with a visual interface and then use DPF behind the scenes. A quick word about the framework, because now we've discussed what DPF is, what it looks like, and what it is useful for, but it is also a framework. So we built it basically with a DPF C++ kernel, which is at the center of everything. And then you have what we call plugins, which bring their, let's say, each brings a set or library of new operators dedicated to a specific task. For example, we have a CFF plugins, which enables operators to read CFF files like Fluent files or CFX files. Then we have EMEA plugin, which enables with readers for EMEA results. HDF5, which brings operators to read and write to HDF5. We have Dyna operators, mapping operators. And so the idea is that this is extensible. You can create your own plugins, you can create your own operators, and this is always expanding. Yeah. So we have the core, the server with its plugins. Let's think of it as a customizable installation of a DPF as a tool, and then you can communicate with it with different APIs. So we have a C# API, which can use via IronPython within mechanical. I'm not necessarily going to discuss that because it's not the topic of today, but again, you can find more information in the documentation about that. Then we have also a C++ client, or I mean, you can include C++ headers in your C++ projects to directly communicate and use DPF via C++. And then we have the client of interest today, which is PyDPF-Core, which is, as the name intends to suggest, the core library, which basically just exposes features available on the server side. So you can create operators, build workflows, do a lot of things with physics agnostic APIs, let's say. And then built upon these generic client APIs, we have a set of different libraries, which are also expanding every day, which are dedicated to different use cases. For example, we have PyDPF-Post, where we have post-processing and physics-based APIs. For example, with an interface dedicated to interacting with LS-DYNA files, an interface dedicated to interacting with EMEA files, or depending on the sort of physics and analysis type you want to treat, we have dedicated APIs to be a bit more user-friendly for people who are not necessarily interested in scripting a lot and building workflows, but just want to post-process files very quickly in an automated way. We have a PyAnsys sound, which just got out, which is a dedicated library, let's say, dedicated to treating and post-treating sound data. Then we have PyDPF Composites, which is a library dedicated to post-processing and treatment of composites, multi-layered shells, all of that nice stuff. So again, this is all accessible in the doc. I shared a few links in the chat if you're interested. So yes, this is just a slide to talk about the fact we have plugins, and then a quick recap on DPF strengths. So DPF is an independent tool. I think it's quite important to stress that out. You can install it by itself. For example, if you just want to open results files you already have in an automated way and post-process them, this is very useful. We are also shipped in any Workbench installation that you have on your computer. So if you already have an Ansys installation on your computer, you already have access to DPF. You don't have to install anything additional other than let's say the PyDPF libraries you are interested in your Python environment, of course. And so DPF can be seen as sort of a glue you can use if you want to have different simulations interact, like if you're doing multi-physics stuff with different, you can use PyFluent on one side, EMEA on the other side, and have them communicate and exchange data via DPF. All right, I'm gonna skip the rest. I think it's a bit self-explanatory. And so, um, just to go quickly over how you can actually use DPF via Python. So, as we mentioned already, we have the PyAnsys ecosystem. I just shared the link again, and we have a few PyDPF related libraries. So the core, again, which is a generic one, then Post, composites, and sound, which are dedicated to different, let's say, use cases. PyDPF-Core, again, is physics agnostic, so if that's what you're interested in, this is the one for you. We have advanced APIs which expose all of the solver features to create and manipulate operators and workflows. The list of supported file types, if you only want to read result files, is in the documentation. I just stated them again here. You can notice that we support MEPDLs, Dynafluent, and CFX files mostly. We do have other features related to, let's say, HEF5 and other common formats. That is all explained in the documentation. You can notice that we don't have AEDT format files here, and I will mention that again in the roadmap. PyDPF-Post, so I just wanted to have a quick review of PyDPF-Post because it's, let's say, the entry-level library for people interested in doing processing with DPF. It is the entry-level and user-friendly library in the way that it's domain-specific. We built it around a simulation object, which you have different flavors of. So, for example, the static mechanical simulation object, a transient mechanical simulation object. You have a fluid simulation object, and each of those presents a specific API dedicated to the use case you may be treating. So the wording, the vocabulary you're expecting is there. And so we have thermal and electric domains in the roadmap. Yeah, so the main data holding object is not a field, but a data frame. The goal was to mimic a bit what you can find, for example, in pandas. So, I mean, it's not as extensive as a pandas data frame, but the idea is for it to behave a bit like it, and we are always trying to expand and improve on this object. So you can think of PyDPF-Core as wrapping NumPy arrays, whereas PyDPF-Post will try to behave like pandas data frames. So this is what PyDPF-Post will look like if you start using it. So you have all of your imports. When you start, for example, you build a static mechanical simulation based on a result file. We provide quite a few in our examples modules. And then you can see that you will have autocomplete present or entering present to you a lot of different APIs available. So we have hard-coded APIs for the different results you can imagine, so that you can know what to expect. And so you can see here, for example, in a static mechanical simulation, we expose a given list of results, whereas in the transient mechanical simulation, we offer other dedicated result and APIs, which are a bit different, again, in their signature and in the vocabulary and the parameters you can give. So very domain specific, let's say. Yeah, again, just showing the signature so that people who are used to reading signatures can understand the difference. I'm going to skip over that quickly. And again, this is an example showing what the data looks like if you print it out using the PyDPF-Post. So you can, for those who are familiar with pandas, this is a very similar sort of structure with indexes or indices in columns, then other as rows, and your data in the middle that you can select based on different filters you can set on the indices. All right. I thought I didn't have time to cover the fact that we can do custom operators and plugins, but just very briefly, you can build your own DPF operators if you want to have reusable, let's say, reusable blocks in your company. You can code them in C++ and build, let's say, package them as plugins and have your DPF installation consume it directly and load it as a customizable installation, let's say. Or you can build your operators in Python and also have the server load them via a specific interface that we have. So you can also build your Python plugins for DPF with a your own custom library of operators and share that across your company. Quick mention of the future and what to expect in DPF. So this is not exhaustive at all. I just wanted to mention the main 2 points, which is that we don't support yet reading in data from electromagnetics with Maxwell and HFSS. This is planned for next year. And we also realize that not everyone is very fond of scripting, and DPF does not have a UI. So we are working on providing what we are going to call flow diagram, which is going to be a UI, an application available to build your workflows. Thanks to a UI, maybe you cannot really read what's in there, but basically you have your library of operators here. You can define input data. You have a small helpers to describe what the operator does and how you should connect it, and then you can just create your own workflow and run it from the UI. So I hope this was a bit clear, and don't hesitate to ask questions next time. We're also gonna have time for those who are gonna come to Lyon. I'm gonna be there to exchange around that if you're interested. And yes, that's it for me.